Hello everyone. I am Amlan Basu. I have recently completed my Ph.D. from Department of Electronic and Electrical Engineering in University of Strathclyde, Glasgow. Today I am going to present my accepted research paper titled Three-Dimensional Object Recognition Using One-Dimensional Capsule Neural Networks at International Conference on Emerging Techniques in Computational Intelligence. Let's start with the introduction first. So, why we have done this particular research? The gaps that we have found in this while pursuing this research is the lack of accuracy in object recognition systems, uh, and also there is a lack of reliability of automated systems in doing object recognition. This is the first gap that we found. Moreover, the deep neural networks for recognizing indoor objects from 3D images, it's still a bit complicated task. Further, the number of parameters are too many when the deep neural networks are implemented for this particular task, and this increases the training time. Therefore, the computational costs also increase. Moreover, there is a very much lack of larger data sets for indoor home objects, particularly. Therefore, this makes the training task very difficult. Therefore, what we have tried to do is we have tried to implement 1D array format data set, and we have developed specific 1D CapsNet architectures to lower down the total number of parameters and to make the training faster and accurate. And for this task, we have used two available datasets that are ModelNet 10 and ModelNet 40. Coming to capsules, why we have used capsules? So if I talk about capsules, it has three basic functions, which we can see that once the input is there, it goes through affine transformation, then it goes through weighted sum, then the squash function, and then the output. So the main reason behind using capsule is the presence of affine transformation, and this affine transformation actually helps capsules to capture the relationship of different objects or the feature of the objects so that the orientation can be captured properly, because feature extraction is not the only task that is needed to be done by the neural networks. Also the orientation, capturing of the orientation of those features is very, very important. So for this, we have used capsules, and this also makes one thing advantage is that we don't have to go for any kind of data augmentation process. Whatever data we have, we can just produce it to the neural network or the capsule neural network, and through affine transformation, it can capture the orientation of the objects from different angles by rotating it or by shearing it. All these kinds of functions that it is able to do. Through that, it does it, and it is able to capture the orientation of any particular object shown from any angle. That's the main reason behind using the capsules. Now, before going on to designing the 1D capsule neural networks or the architectures of 1D capsule neural networks, what we tried to do is we tried to integrate the point net architecture with the capsules. Why we did is because we wanted to study how the capsules behave on an already existing architecture that can be trained directly on the raw 3D data set, that is on point cloud data set, and what kind of accuracy we get, and then we can decide how to approach for this. However, it did produce good accuracy, but not as per the expectations. So therefore, this gave us a motivation to further develop 1D capsnets. So these are the two different architectures that we developed. We tried this architecture in different ways. The main thing that we tried to do here is bringing in the max pool layer with capsules. So we tried to put the capsules at every layer, and we even tried to use more than one number of max pool layers, but these were the two architectures or the designs that produce the best accuracy and the best parameters. So what happened here, why we while we place max pool layer after all the convolutional layers, that was a good accuracy, but as soon as we place the max pool layer just after the two concatenated convolutional layers, the accuracy increased. The hypothesis from this that we formed was that the objects have more minute informations or the features to be extracted. Therefore, here, if putting the max pool layer just after the extraction of small features, what happens is max pool layer helps us to extract only the important information from the extracted information of convolutional layers, and then it sends that extracted in the important features, the only important features, to other layers, the further layers of convolutional layers, where it becomes easier for the layers to deal with the filtered information and get the higher level features extracted. And you can see that we have capsule layers here, 1D capsule and 1D class capsules. Then we have the fully connected layers, and we have used softmax layer for the last classifications. And definitely we have used the concatenated convolutional layers, that is, we have used the convolutional layers in parallel so that we can establish a parallel computing so as to make the training faster. The results. So the results are like, we have the 1D CapsNet B has reported the highest accuracy among the architectures that we have tried to develop. Well, definitely it is bit lower to as compared to rotation net, and also a bit lower to 3D capsules. But what we have compared is that the total number of trainable parameters, we have only 1 million trainable parameters, whereas rotation net, that has the highest accuracy, has 5 million parameters. So we have total number of trainable parameters 5 times lesser as compared to the rotation net. Definitely point net is a kind of MLP and all those things, so it will have definitely lesser parameter, but at the same time it has compromised with the accuracy, especially on model net 10. So that's what we have improved. We have uh, acceptable total number of trainable parameters, and as well as we have acceptable accuracy. So at the same time, we are not using the multi-view images, means we don't use the data augmentation. We are not doing any kind of data augmentation by taking the pictures of same images from different view angles and making the data set bigger. At the same, moreover, we have the architectures that we have developed. They don't require any kind of conversion from point cloud raw data set, that is, to 3D voxel grids. So these are some of the advantages that we have been able to achieve from these architectures. In conclusion, that we can say that we have developed two decent capsule neural network architectures, and we have, through those, we have successfully reduced the total number of trainable parameters. At the same time, we have reduced the training time without affecting the accuracy much. We have the acceptable accuracy. We are in the acceptable accuracy range, and also we have reported higher accuracy on very small data set, just 5,000 images, and uh, just 5,000 images we have, and we have been able to produce above 90% of accuracy. We have not used any kind of multi-view images of a single object, and the architectures, which are the conventional architectures we have, it can be trained on directly on raw point cloud dataset. And we have also proved that capsules with Maxpo layer, if used with Maxpo layer, produce better accuracy as compared to using only capsules. These are the conclusions that we have derived from our research. Thank you very much. And if there is any question, it is very much welcome. Thank you.